welcome to our lecture on the foundation of offline reinforcement learning. I am a researcher at MSR Montreal, and this is a shared talk with David, who is a PhD student at New York University. So the tutorial is split into 3 parts. First, I will provide some background and the motivation of offline reinforcement learning. Second, David is going to exhibit the failure modes of the non-specialized approaches. Third, I'm going to construct a cartography of the specialized algorithms. Fourth, David will go over some benchmark environments for offline reinforcement learning. And finally, I'll conclude. So I start with background and motivations. First, by introducing reinforcement learning, then offline reinforcement learning, and finally, the different objectives we may go after. So reinforcement learning is like climbing a mountain. It's dangerous and it requires some planning ahead. We'll use a lot this analogy, but first let's delve into real applications for reinforcement learning. So reinforcement learning is learning to make sequential decisions. Potential reinforcement learning applications list is expensive. Robotics for drone control, dialogue systems such as personal assistants or call centers, in the game industry to control non-player characters or computer AI in general, for treatments such as pharmaceutical tests or crop management, or again for complex system control, resource allocation, flow optimization, you name it. So here is an illustration of the reinforcement learning process. The learning agent takes an action. This action has an effect on the environment, and the agent perceives a new state of the environment and receives an immediate reward. Let me illustrate it further with a video game, Super Mario Bros. This is the environment from the learning agent's point of view. The agent's action is performed on a virtualized controller. The state is the video output of the game, and finally, the reward is the score, or rather, should I say, the points added to the score. Algorithmically, it is very simple. Perception, action, reward, and then it loops. But it's a stochastic process, meaning that two trajectories at the same two trajectories of the same agent in the same environment starting from the same state may be different. Basically, every step may have a random component. The environment may react differently to the same actions. Easy to comprehend in a dialogue setting where every user would react differently, use different words, and say those words differently. The agent may also choose different actions in the same state. And finally, the reward may also be randomized. So the objective of the learning agent is to pick actions so that the cumulative rewards are maximized. In the Super Mario Bros. Example, we want to maximize the score. Now we are going to formalize the task and produce some useful concepts and their notations. So we will model the environment with a Markov decision process, MDP. It's a tuple of 6 elements. A state set, X, an action set, A state initialization, P0, which is simply a distribution over the states, a transition function, P, which determines in which distribution of state we will end up after taking some action in a given state, the reward function, which will determine the immediate reward we get from taking some action in some state. And finally, the discount factor will define how much rewards that we collect in the future will count. We will also model the behavior of the agent with a policy. A policy is a function that takes as an input a state and returns distribution over the action. And now we want to be able to evaluate the policy. And to do so, we'll compute the return of a trajectory. And the return of the trajectory is the discounted sum of the rewards collected at each time step. And here we see the role of the discount factor gamma. It tells that future rewards are going to be geometrically discounted in the return perceived at time t0. Now, given a policy pi, we want to be able to compute its value in a given state. And what it is, it's simply the expectation of the return when the trajectory starts from this state. There is also the state action value, which is denoted by Q, which is still the expectation of the return, but under the conditioning that the starting state is X and the starting action is A. And finally, we'll be considering the performance of a policy, which is once again the expectation of the return, but under the conditioning that the initial state is sampled according to the state initialization of the MDP. And it can be also written as the expectation of the value of x0 being sampled according to P0. And now, what is the objective under this formalization? It's to find a maximizing policy. Pi star that will maximize the performance over all the possible policies. And there is actually a very nice result that shows that this policy is also going to be the one that maximizes the value in every state and the state action value in every state action pair, for every state action pair. Now we are going to do a rapid overview of classical reinforcement learning algorithms. We frame it under a generalized policy iteration framework. It consists in a loop over 2 steps until convergence. An evaluation step, where the current policy is being evaluated, and an improvement step, where the current policy is updated on the basis of the current value. Classic policy iterations evaluation step is the exact evaluation of the current policy, meaning that Qi is equal to the value of pi I. So that's what we've written Q pi I in the previous slide. Classic policy iterations improvement step is the argmax of Qi. The policy is being greedy with respect to the current value. Now, the interesting thing is that Q-learning may also, or SARSA, may also be represented in the policy iteration framework. Its evaluation step is the Q update based on the Bellman optimality error for Q-learning or the Bellman evaluation error for SARSA. And its policy update is the argmax, like for classic policy iteration. And actor-critic algorithms may also be framed with the generalized policy iteration. The evaluation is the update of the critic for actor-critic algorithms, and the policy improvement is the policy update step. So we've just introduced reinforcement learning, or rather, should I say, online reinforcement learning. Now let's see offline reinforcement learning. You see that the line has been removed, so it looks even more dangerous now. And let's see why. So first, I want to remind that this talk is a lecture. This lecture is a tutorial on offline reinforcement learning, and sometimes we also call it batch reinforcement learning or fixed dataset reinforcement learning. In contrast to the classic setting introduced in the previous slides, the learning agent does not interact directly with the environment. Instead, it's a behavioral agent that is used to collect data. The trajectories are then stored and then fed to a batch reinforcement learning algorithm to generate a new policy. So from a fixed set of transition samples that we will denote by D, which is a collection of transition X, A, X prime R, where X is the state at the origin of the transition. A is the action that has been taken in X. X prime is the state at the end of the transition, and R is the immediate reward. So from a fixed set of transition samples collected under some behavioral policy beta, we want to generate a high expected return policy pi. But the true MDP M star is unknown, and trial and error cannot be used as generally we do in online reinforcement learning, meaning that if we do a mistake, we cannot update the policy and correct this mistake. So we cannot learn from the error that the policy that we generated is going to make. So that means that offline reinforcement learning cannot resolve this epistemic uncertainty it has about M star. It only has some trajectories and it has to deal with it. So let us review when offline reinforcement learning is required in the list of reinforcement learning applications we've seen before. For robots, most of the time online reinforcement learning can be used, so we don't really need offline reinforcement learning. For dialogue systems, and it is comparable to the game industry, updating the models is not practical. One cannot update the policy online. It is too costly in terms of networks and computations. The policy update may only be performed once a week or a month. For drug treatment or crop management, the timescale is so long that one cannot wait the end of the year to get a sense of what has been a good behavior and what has been bad. One must therefore rely on offline data. And finally, for complex systems control, there are often security control involved, and one must be able to validate the safety of the policy before implementing it. So I would also argue that offline reinforcement learning is impactful. So I start with a small disclaimer. In many of our considerations, we are going to consider finite MDPs, meaning that the set of states and set of actions is going to be finite. And we do so even though we are interested most of all of complex environments, so that are not finite. We are going to do so in order to induce some intuition on desirable features, and also to show some negative results that we already have with finite MDPs. So since the only source of information we have is the dataset, we'll need to define some dataset-centric quantities. So first, the number of trajectories that we will denote with capitalized M, the number of transition samples with small m, the state count, which is the number of times state X has been visited in the dataset. State action count, it's the number of times action A has been performed in state X in the dataset. And state action state counts, which is the number of times we transited to X prime after performing action A in state X in the dataset. We also consider the behavioral policy estimate, beta hat, which is simply the ratio of time we perform A in state X for every time we've been in X in the dataset. And likewise, we will consider the maximum likelihood estimate of the environment, which we will call MLE MDP in short, and write M hat, which estimates the initial state distribution as the number of time X was the initial state of the trajectory divided by the number of trajectories. State transition function is the number of time we ended up in X prime after performing A and X divided by the number of times we've been in A and X. and the reward model, that is simply the average reward that we got after taking action A instead X. And yeah, I'll finish this introduction of offline reinforcement learning by saying what we will not deal with. So first, I want to make sure that you understand that offline reinforcement learning is more than off-policy reinforcement learning. Off-policy reinforcement learning consists in training a policy under samples coming from another policy. Obviously, that's what we're going to do because we want to plan a new policy that is better than the behavioral. And so that is different from the behavioral and from samples that have been collected exclusively with the behavioral. But off-policy reinforcement learning does not account for the risk of generating bad policies. And this is the big issue with offline reinforcement learning. Second, we do not cover the more specialized setting. Sometimes we want to iteratively collect more data with the generated policy. So I have a first data set, I generate a policy, then I collect more data with the new policy, then from which I can generate a new policy and so on and so on. This is referred in the literature as multi-batch reinforcement learning. And this is actually a setting that would be useful in the dialogue setting or in a game setting. Sometimes we also want to implement fast online adaptivity, meaning that we train a first policy offline, and then we want to adapt quickly to bad outcomes that we observe while playing it on the true environment. This is also something that would be very interesting in specific applications. The problem with this setting is that even that they are often closer to the real world, they are also harder to standardize. And we would need to be really confronted to a specific application to really design what is the exact setting. So we are not going to cover that, and we are going to stick with pure offline reinforcement learning. So we've got a data set and we want to generate a new policy. So what are we after? How can we compare offline reinforcement learning algorithms? So the goal is ultimately to maximize the infinite discounted sum of rewards in the true environment, as we've seen before. But this objective is with respect to m star, which is unknown. It's an unknown quantity to us. So we only have the data set D. Therefore, we will modify a bit the objective, and we will say that we want to optimize the expectation of the performance of the policy under the knowledge of the dataset D. So here, m star can be treated as a random variable. And this is what we call the expected performance maximization objective. Alternately, we may also consider the expected policy improvement maximization objective, where now we want to maximize the performance gain that we get in comparison to that of the behavioral policy. We may also want to minimize the expected regret, which is the difference of the performance of the optimal policy in F star and the policy that we returned. And they actually admit all the same optimal solution because we can see that JPI is actually equal to JP minus some quantity that is independent of pi. And in the same fashion, JRM is equal to some quantity that is independent of pi minus JP of pi. So the target policy we're after is actually the argmax of JP or of JPi or the argmin of JRM. So I have finished with the first section, and now I will pass the ground to David. Okay, so
okay, I think I'm live now. So the second section is going to be about the limitations of non-specialized approaches to this offline RL problem. So there we go. So going back to the climbing analogy, you might think that the problem with running an online RL agent when you're actually offline is that you're liable to sort of fall off of the wall. So while it might be intuitive that sort of we have all these nice online RL algorithms, running them naively in the offline setting can cause problems. And that's sort of the first thing we want to talk about. Okay, so what is the approach? What are we considering here? So the idea is like, okay, we could run an online RL algorithm on the data set that we have, just pretending that the data set was coming in from the environment interactively. But unfortunately, any online RL algorithm will find exactly the same policy. And intuitively, this is just the optimal policy in the maximum likelihood MDP. So basically, because what the online algorithm is trying to do is just to maximize the rewards, it will maximize the rewards in the empirical MDP induced by the data set. So we'll call this the greedy algorithm. And we'll denote it by pi g, and sort of pi g is the argmax over the set of policies of the expected cumulative return of the policy pi in the empirical MDP m hat. Now there exists a nice sort of theoretical suboptimality bound on this algorithm, which tells us that the difference between the expected cumulative return of the optimal policy in M star, the true MDP, compared to the expected cumulative return of our pi g in the true MDP M star is bounded above by this quantity shown here. Now, the sort of important part of this quantity to notice is that in the denominator, we have a term that depends on the minimum over the state and action space of the count of visiting that state and action. So you could imagine if there's a case where there's some state and action that we haven't seen at all, that then this bound is completely vacuous. And even in the case where we've seen every state and action, if there are some states and actions that have only been seen very rarely, this bound can be really large. So intuitively, how do we explain this? The main failure mode that we're worried about is this sort of case where there are rare but risky actions. So first, let's go through sort of the simplest possible setup that sort of illustrates this issue. So consider an MDP with a single state in two actions, A1, A2. We'll let R1 star be the reward of taking action 1 and have it be deterministically 1. So you always get 1 for taking action 1. And then for taking action 2, you get R2 star, which is going to be stochastic and distributed uniformly between either -2 or +2. So half the time it's -2, half the time it's +2. Then we're going to assume that the behavior policy is sort of adversarially defined for this example to choose the action A2 with probability 1 over n, where n is the size of the data set. So when we choose the policy this way, we know that we'll see exactly one sample of A2 in our data set with probability at least 1 over e. This is just by sort of the binomial distribution. So the sort of key idea here is that action 2 is risky, so it's sometimes good, better than action 1, but often, but sort of equally as likely it's bad and sort of much worse than action 1. But it's rare, so we don't see it very often in the data set, and so it's hard for us to get a good estimate of how good it actually is, because we maybe haven't seen enough data to determine whether it's good. And specifically, if we've only seen it one time, we either saw a 2 or a -2. If we saw a 2, we think it's actually very good to take action 2. If we saw a -2, we think it's actually very bad. So more formally, we can see exactly one sample of A2, then pi g, the greedy policy, will select A2 with probability 1/2, so that, applying this probability of 1 over e of having this case where we only see one sample of A2, we see that the expected cumulative return of the greedy policy in this problem is bounded above by 0.82. And this is even though the expected cumulative return of the behavior policy beta is 1 minus 1 over n. So for example, if we had 100 samples, that would give us, 0.99. So in effect, the greedy policy has done now much worse than the behavior policy that we were starting from, because it sort of decided to choose this rare but risky action. So, okay, you might be thinking, can the same thing happen in sort of a less adversarially constructed example? So this example was sort of very clearly constructed to sort of have one action that was very rare and very risky. So the answer is yes. So here's an example that's maybe slightly less adversarial, but sort of still has sort of the same flavor in a grid world environment. So a 2D navigational task where the state is your sort of position in 2D space. So you could imagine that we could have the expected reward like so. So here along the left wall and the bottom wall, I have that the expected reward is negative, but those states are noisy. So they're going to give stochastic rewards every time I visit them. And then I have a deterministic good state in the top right corner. Now let's say we take a uniform behavior policy. So here I'm using the arrows to illustrate the behavior policy. So the size of the arrows correlates with the probability of taking each action. And then the colors show the value function. So the colors show starting at this state, what is the expected cumulative return going forward, rolling out under this behavior policy. So you can see that the behavior policy sort of gets slightly higher values when it's near the good state, but generally sort of pretty uniform. Now, when we collect a data set, so say we collect 1,000 data points by sort of running several rollouts under the behavior policy, then we get some empirical rewards. And because the rewards along the left wall and the bottom wall were noisy, we're going to have sort of poor estimates of those states because we maybe don't have enough data to estimate them exactly. So some of them will be overestimated, some of them will be underestimated. And then we try running the greedy algorithm on this data set. When we run the greedy algorithm, we get some policy like this. So in this case, also for clarity, I'm using a discount of 0.9. So sort of the effective horizon is something like 10 steps. But what happens basically is that the states that have been overestimated, the greedy policy is attracted to because it says, well, I can get more reward by going towards those states. But in effect, this is going to harm the value, as you can see by the color. Sort of, you can get these very dark blue colors because the value is going to be negative for seeking out those states, because those states were in fact like had negative expectation. So basically, this is just showing the same effect that we saw before, which is that like if there are sort of poorly estimated states and actions in your MDP, then running the greedy algorithm has the liability to sort of choose those actions over the good actions. So maybe more generally, how can we think about this problem? And the idea is basically to think about this idea of distributional shift. So more specifically, the distribution that we're considering that might be shifted is the sort of distribution over states and actions induced by the policy. So we can call it the discounted state action distribution of a policy pi. And this is defined here, which is basically the cumulative discounted probability that sort of state T and action T are equal to X and A when we're rolling out a policy pi. Now, the performance of the policy can be written as an expectation under this distribution, literally just the expected reward under this distribution, which can also be expanded as the sum over states and actions of this state action distribution times the rewards. Now, importantly, the distribution of the behavior policy beta is not equal to the distribution of the greedy policy. And that's sort of fundamentally what's causing a lot of these problems that we're seeing in the examples. So states and actions that are rare under d beta are poorly estimated. And then since pi g naively tries to maximize estimated performance, regardless of the quality of the estimates, it sort of seeks out estimates that cause sort of overly optimistic estimations of those states and actions. So basically, this is the problem that we're seeing in these examples. And this is sort of why running online RL offline can cause problems. So one idea that you might use sort of from supervised learning or sort of other areas to try to fix this would be to use maybe a train validation dataset split, because somehow this issue does look something like in a sort of overfitting because we're using this greedy policy. So how would this work? So this is an idea that's in the literature. They call it a high confidence policy improvement sort of takes this approach of doing this train validation split and then running some sort of like cross-validation type procedure. Okay, so how does this work more precisely? So to deal with the overfitting risk, we can try splitting the data set. We can use the training set to generate a set of candidate policies, then use the validation data set to evaluate each one of the candidates, and finally select the policy that has the highest lower bound on its performance. So in this case, to sort of, because we maybe don't trust our estimates that we're getting from this validation set, we're not going to use them naively, we'll use a lower bound of them to sort of be more robust to these estimation errors. So this technique relies on basically two steps. First is the generation of these candidate policies, and second is the off-policy evaluation from the validation set. And sort of we'll look at sort of maybe how we do each one of these steps and why there could be sort of some issues with trying to figure them out. So here we'll just consider the set of candidate policies that was in this HCPI work. And they propose basically to interpolate between the behavior policy and the greedy policy. So you can just take linear mixtures for some mixture weight alpha between the behavior policy and the greedy policy. So when alpha equals 0, this is exactly the greedy policy. When alpha equals 1, this is exactly the behavior policy. So this assumes knowledge of the behavior policy, or at least a good estimate of it. And since the case where alpha equals 1 is exactly the behavior policy, this algorithm is attempting to do some sort of safe policy improvement, right? It's trying to consider which policy would do better than what I was doing before. So we don't have this issue where we act too greedily and end up being much worse than we started off. Unfortunately, the mixed policies might perform worse than both of the extremal policies, than both the greedy policy and the behavior policy. And in general, it's unclear sort of how to create a set of candidate policies with a relevant spectrum of risk. So that's sort of the first step. We generated some candidate set. Now, the next step would be, and the sort of more difficult step, is that you need to do the offline policy evaluation. You need to figure out which one of these candidates is actually any good. And this sort of comes back to sort of the same problems that we saw before about sort of what happens when you're offline. So let's delve into it a little more formally. So how would we do the offline evaluation? So you could see that the cumulative return maybe can be written as the expected return for the trajectory, conditioned on the trajectory being generated by pi. We can write this out as a sum over all possible trajectories of the probability of the trajectory times the return on that trajectory. And then we can sort of do importance sampling to correct for the distribution change. So remember, we only have data generated from the policy beta, but we want to evaluate what happens under the policy pi. So we can correct for this by using some importance sampling. And then we can go from this sort of infinite sample regime where we're summing over all trajectories to our finite samples, which are our data set D, which are generated from beta. And so then we're able to sort of come up with a way to actually estimate this. So unfortunately, the problem is that this has very high variance because the variance grows geometrically with the trajectory length. So you can sort of see this intuitively that this probability of a trajectory is really a product of probabilities of each transition along the trajectory. So when you take this ratio of products, things can blow up pretty quickly. So fundamentally, this is the same issue of this distributional shift problem, which is that if you're trying to reach some states and actions that beta doesn't cover well, these importance weights are going to blow up, and this is going to cause very high variance. There are a lot of papers that work on sort of improving this bias variance trade-off that we're not going to survey in this tutorial, but fundamentally, they all sort of still face the same issue, which is that there's this distributional shift problem, which makes this offline evaluation very difficult for policies that differ from the behavior policy substantially. So this is sort of a summary of what's going on when you take these sort of more naive approaches that you might have thought of from standard RL or from supervised learning. And now Romain's going to talk about some more specialized approaches for offline RL.
Thank you, David. So thank you, David. Now I will present approaches that are specialized to deal with offline reinforcement learning. And I propose to categorize them into 4 classes of algorithms. multiple MDP algorithms, pessimistic algorithms, conservative algorithms, and early stopping algorithms. We'll come later to explain what this means. So you remember the generalized policy situation that we presented in the background section. There, the algorithms train iteratively the policies through improvement and evaluation until convergence. And we showed that it contains the most famous algorithms from Q-learning to actor critic. Actually, I would argue that most, if not all, 9 RL algorithms fit into it. However, it appears that this framework is insufficient to categorize all the algorithms in the offline reinforcement learning literature. We are therefore going to introduce the Bayesian policy iteration framework, which takes into account that the true MDP is unknown. In the Bayesian policy iteration figure, each cloud represents an environment, and the stack of clouds show that not a single MDP is going to be considered, but many of them. We use the term Bayesian to qualify the framework because the inference of the plausibility of an environment may be performed through the Bayes rules. This framework will allow us to articulate a comprehensive cartography of the existing algorithms. So we categorize algorithms as follows. Multiple MDP algorithms contemplate the multiplicity of the plausible MDPs. These algorithms will optimize the policy with respect to distribution of MDPs instead of a single MDP. Pessimistic algorithms transform the value function with the component penalizing taking action with high uncertainty. These algorithms are called pessimistic because they see the value of their state at the worst possible given its uncertainty. Conservative algorithms constrain the set of candidate policy in such a way that it remains close to the behavioral policy. These algorithms are called conservative because they change their policy only if it is for the better. And finally, early stopping algorithms apply a limit in the number of updates allowed to train the new policy. We start with multiple MDP algorithms. In this class, the climbing learner will contemplate all the potential mountains that the environment may be and choose a policy that fits the best. So we start with the naive Bayes algorithms, which consists in optimizing the policy by sampling MDPs according to the posterior and taking the gradient of the policy in it. I won't go into the details on how this gradient is computed and the technicalities here. What I will say that the naive Bayes algorithms has numerous issues. The first problem is that it's not a convex problem and it has plateaus, so that following just the gradient might push us into might prevent us from converging to the optimal solution. The second issue is that it's highly intractable. The gradients have high variance and a policy is a too complex object to maximize in such a holistic way. Also, there are strong priors that are difficult to induce. In particular, the performance of the behavioral is generally assumed to be high, or at least better than any arbitrary policy. And this is very hard to induce such a bias with this formulation. Another approach are robust MDPs. They can be regarded as an approximation of the Bayes formulation by partitioning the MDP space into two subsets. The subset C of plausible MDPs given an uncertainty measure. So we are going to consider that the transition function must be into some range of values. And the complement, we'll also consider the complement subset of implausible MDPs. And actually, the safe or robust performance objective is to search a policy that maximizes the minimal return over the plausible set. Formally, it's written like that. So we're looking for the policy that yields the minimal performance in the set of plausible MDPs. And we finish this section with the safe policy improvement objective. So the robust behavioral maximizes the minimal improvement over the behavioral policy, considering all the plausible MDPs. In other words, the algorithm looks for the policy such that the worst improvement gap with respect to the behavioral policy will be maximized. So this approach has for advantage to take as a reference a known quantity that is the behavioral and solve partially the bias that we have about the performance of the high performance of the behavioral policy. But it's a problem that is NP hard to solve. And there exists some approximate heuristic, but they don't have any formal support, and they still remain complex computationally. And so we've seen that while in introduction, we've seen that expected performance and expected policy improvement admitted the same optimal solutions, their robust and safe counterparts may yield very different solutions. So now let's sum up the strengths and weaknesses of the multiple MDP approach. So first, the strength. It's theoretically sound, and it is also influential as ideal solutions. But it also has weaknesses. It's computationally intractable, even in small finite MDPs. An approximate solution are not well, the approximate solutions are not well supported by theory. And finally, there is the unsolved problem of how to incorporate the bias that the behavioral is high performing. So now let's move on to pessimistic algorithms. So in online reinforcement learning, an agent can afford to be optimistic and look up the mountain, since every failure turns into a valuable lesson. However, in offline reinforcement learning, the agent is not allowed to learn from its mistakes, so it must really take care of the risk of falling. And this class of algorithms reflect this. So we class in this category all algorithms that artificially alter the evaluation of the policy in the environment. This approach often builds on some uncertain estimates, U of XA, to alter the reward function. So I recall that R hat is the best estimate that we have of the true reward function of the environment. And we penalize it with some weight lambda according to the uncertainty we have, to some uncertainty measure we have. The principle is quite intuitive. We consider that any source of uncertainty would equivalently manifest as an immediate risk. And this is a way to characterize the worst case MDP and to find a policy that maximizes it. So it can be seen as a tractable approximation of the robust MDP approach that we've seen right before. So what are the strengths and weaknesses? It's a symmetrical formulation to optimism in online reinforcement learning. So we can build up on work that has been done with optimism in online reinforcement learning. It's also easy to implement. We can add a regularization. We just have to add a regularization term to the reward function. And finally, it's consistent, meaning that if we get infinite data, it will eventually converge to the optimal solution. We can see that because the R hat is going to convert to R star with infinite data, and the uncertainty U of XA will hopefully also decay to 0, such that we're going to plan into eventually plan into the true environment. if we have infinite data. Now, what are the weaknesses? The first one is that it returns a deterministic policy, which is kind of an indicator that it lacks expressivity to balance the risk that it may take by taking some actions. The second weakness is that it's not well grounded theoretically. So it is consistent. So we have some guarantees with infinite data, but with a finite size data set, it is not well grounded. Third, hyperparameters are difficult to tune as they are domain dependent. And fourth, it relies on an uncertainty measure. So we are not going to extend during this lecture, unfortunately, on uncertainty measures. But what I can say about that is that they are very unreliable. It's a very hard task for a network to be able to estimate its certainty or its uncertainty. And the last weakness is the uncertainty propagation dilemma it faces, and that I will expand on the next slide. The first dilemma is with regard to the propagation in depth. And we will consider this small MDP, where one action, A1, terminates immediately, and the other, A2, leads to a chain that will eventually terminate after several deterministic transitions. The uncertainty incorporated in the reward function will be measured every time step and propagated such that the value in A2 is going to be much more penalized than in A1. However, it should not be the case. But we also need to do this propagation in depth to account for further uncertainty, because we don't want to plan to go into a state where every action is very uncertain and where there is no more other choice. Also, it's going to accumulate and penalizing long horizon. So it's an issue because it's going to be a bias in favor to shorter trajectories. And we have the same kind of problem with propagation in width. So we now consider a different MDP with a deterministic red path yielding some small reward. And the blue path that instead transits to a cloud of states, but eventually always terminate and getting a high reward. The pessimistic approach will penalize strongly the blue path because the transitions from the cloud states to the terminal reward are going to be very rare, because every state in the cloud will be encountered once or a handful of times. And it will be penalized strongly. And once again, we're going to propagate this uncertainty to S1. And this is another bias that we have. And still, the outcome is very reliable by taking the blue path, because every time we took it in the data set, we ended up with a high reward. So this is not justified. Next, we'll deal with conservative algorithms, which are bound to remain close to the policies that generated the data set. So we class in this category all algorithms that apply a constraint on the policy search during policy improvement. Some online algorithms, such as CPI, TRPO, PPO, apply such constraints, but these constraints are for stability. They are with respect to the policy in the previous iteration. So when you're computing pi I plus 1, you will do the constraint with respect to pi I, which does not prevent to stray away from safety. So in this section, we'll consider offline reinforcement learning algorithm that ensures that any change in policy with respect to the behavioral, so with respect to beta, incurs an improvement in performance. So we are going to do the same kind of regularization, but with respect to the behavioral policy. And since we are focused on the improvement over the behavioral, it can be seen as an approximation of the robust behavioral regret that we talked in the multiple NDP algorithm section. So the first algorithm we're going to talk about is batch constrained Q-learning, BCQ in short. It implements a policy search that is constrained according to some hyperparameter epsilon. And it's very simple. The constraint is that we are going to only consider policies for which that is equal to 0 when the behavioral is small. So if for some action in some state the behavioral is small, then we are going to force the policy to be equal to 0. And then we search for the policy in this set that maximizes the performance in the MLE MDP M hat. So BCQ has 3 shortcomings. First, the set of the first problem is to set the policy to 0 when the behavioral is small. Actually, it should instead set it to beta. Even though we have the bias that the behavioral is strong, it doesn't mean that there might not be actions that the behavioral takes only rarely that are better. So we don't need to put it to 0. If it's already small, we can keep it small. The second issue is that it does not adapt well to the actual amount of knowledge collected in each state action pair. So we may have a lot of data in some states, so that even for an action for which the behavioral is small, we have a lot of data. And in this case, we should be able to learn and to modify the behavioral. And finally, with a fixed epsilon, strictly positive, the algorithm is inconsistent because if the constraint is independent on how much data we collected. So if we get an infinite amount of data, we're still going to be constrained in our policy search. Now we move on to another algorithm that is called conservative Q-learning, CQL in short, which optimizes the following reward in the MLE MDP. So it's the estimate of the reward minus lambda time the ratio of the policy that is currently being trained and the behavioral policy. So it functions like pessimism, right? We have a penalization of the reward function, but it actually behaves like conservatism because the ratio of the policy we are training is not some form of uncertainty. It's more a constraint on pi to remain close to beta. And we see here that if we set pi to be equal to beta, we don't have any penalization at all. And if we change pi, it's actually going, we can show that it's actually going to penalize the trained value. So yeah, CQL can be viewed as arguably a bit both, a bit pessimism, a bit conservatism. CQL can also be interpreted as a soft-version of BCQ, but it performs much better in practice. The softening of it makes it very valuable. And finally, I'll briefly talk about Combo, which is a model-based version of CQL that improves further the performance in some benchmarks. Now, the last algorithm that we are going to consider is called safe policy improvement with baseline bootstrapping, SPIB in short. It applies constraints on the policy search according to the following principle. It is allowed to change the behavioral only when it is confident, statistically confident to improve it. In practice, PIB constrains the policy in a way that is very similar to BCQ, but there are two very different stuff. Pi is not set to 0 when the behavioral is small. We keep it equal to beta. And the second fix is that we don't set the condition on the constraint on some epsilon and on the policy, but we have this hyperparameter n wedge that is the minimal number of samples we need in order to be able to change the policy. And there also exists a soft version of SPIB that uses an error bound on the MLE MDP, and basically you have a budget to change the policy, which you can spend, and you spend more as you are more uncertain on the action for which you want to change. And both of these algorithms come with policy improvement guarantees, which is nice. Also, there are numerous SPIB extensions. We can estimate the behavioral and still have safe policy improvement guarantees. SPIB algorithms may be applied to multi-objective reinforcement learning with close to no impact in terms of sample efficiency. Also, the guarantees carry out to dataset generated from multiple policies. Indeed, in many applications, such as, let's say, treatment and drug administration, different doctors are not going to prescribe the same drugs. And so each doctor can be seen as a different policies, and there is no issue to using such dataset. And finally, a deep reinforcement learning version has been implemented. So it's not only a finite state algorithm. Now, what are the strengths and weaknesses of SPIB? It's well-grounded theoretically, and it's consistent. It's relatively easy to implement and computationally efficient. And the hyperparameter setting is intuitive and not too sensitive or even domain dependent. It's because the hyperparameter is related to statistical significance, which is some universal law of the numbers. It still has some weaknesses, and the biggest one is that it relies on an uncertainty measure in comparison to CQL, for instance, which does not require. It also relies on a behavioral policy estimate, which is a bit less of an issue, but still a constraint. And we can show that it solved the two problems that we've seen before. So first, the propagation in depth example, SPIB will stick to the policy of the behavioral policy in states S2, S3, and S4. So the choice in A1 versus A2 will be based on their respective unmodified value estimates and the policy constraints in this state. And the same for the propagation in width example. Again, the SPIB will freeze the policy in to the behavioral in the cloud, and the decision in A1 versus A2 will be based on their actual value estimates. So I'm actually going to early stop here and pass the ground to David again.
Okay. So I think I'm live now. Right, so now I'm going to talk about early stopping. So this is something that I've personally worked on, so that's why I guess I'm going to be talking about this part. So yeah, so what's the idea of early stopping algorithms? So we have this loop where we're alternating between evaluation and improvement. And early stopping basically, instead of modifying either the evaluation or the improvement step, just modifies the number of times we're going to go around the loop and basically reduces it. So this is sort of an alternative idea, or sort of a idea that can sort of work with some of the other ideas that we've been talking about already. So this can go as far as simply running one iteration through the loop. So basically just evaluate the behavior policy and take one improvement step from there. This ensures that the evaluation step only needs to evaluate policies that are near the behavior, which prevents some of these issues of extrapolation error. So at the extreme example, if you only take one step, the only policy you're actually evaluating in the evaluation step is the behavioral policy, which you should expect to be able to evaluate pretty well because that's where the data is coming from. And so in that case, you can trust your evaluation a little bit better, and then you take one improvement step, which takes you sort of only one step beyond the data that you have. Now note, this still usually needs to be combined with other offline RL approaches, because if you take one completely greedy step, you can still have all the problems that the greedy algorithm had naively. So maybe just as an illustration here of the sort of simplicity of this approach and sort of an intuitive understanding of what's going on, you could imagine you start from the behavioral policy beta, and you have some set of sort of safe policies nearby beta, where you sort of think, okay, I have good enough understanding of what's going on at these policies that I can evaluate them reasonably. I can like make a good step from there. So sort of the one-step algorithm, which is sort of the extreme version of early stopping, only needs to evaluate the Q function of the behavior policy. So this is on policy data, so this is drawn in blue here in this little drawing. But then every subsequent step, you're going to have to evaluate off policy, and you're going to have to, at the same time, try to remain within this set of safe policies, which is sort of difficult to do in practice. So each one of these estimates, Q hat in red, that is sort of using data different from the data that generated, from the policy that generated the data set, is going to be higher and higher variance, and you're potentially going to sort of lose control over the process. So early stopping sort of has this nice simplicity where it basically just says, okay, well, if more steps is potentially leading to more variance, we'll just take less steps. And this easily combines with the other approaches because we can still sort of use the modifications to either the improvement step or the evaluation step that we were considering before. And empirically, this actually does work pretty well. We'll get to some benchmarks in a moment, but it has strong empirical performance when the behavior policy is sort of not doing a very good job of covering all of the states. So when the behavior policy is fairly concentrated on some part of the state space, this one-step thing is useful to sort of ensure that you're not going outside of the set of safe policies. Now, of course, it also has some weaknesses. So the first being that it's inconsistent. So you're not going to recover the optimal policy with infinite data because you're only taking one step. So if you actually want to find the optimal policy, you need to sort of iterate around this loop until you get convergence. And the performance can be highly dependent on the behavior policy. This is sort of true across many of the different algorithms that we're considering, but especially true here because since you're only taking one step from the behavior policy, the policy ends up being fairly similar to what the behavior was. And again, it doesn't resolve some of the simple counterexamples. So like the one state example that I talked about earlier alone. So you need to incorporate some sort of like conservatism, for example, on top of the early stopping to prevent these examples. Okay, so that was sort of a summary, I guess, of some offline RL approaches that people have taken. And now we'll look at briefly some benchmarks that people have used to sort of try to evaluate these in sort of larger scale problems in the sort of academic literature. So here's some benchmarks. Oops. Okay, sorry. The benchmarking setup is basically that we want a problem to test which algorithms work the best, right? So here by algorithm, I mean sort of something that takes in the data set and spits out a learned policy. And then the benchmark basically sort of provides the data set and then also provides a way to evaluate the learned policy so that we can compare the algorithms. So this has a few challenges. So the first challenge is that test time evaluation is very difficult. So going back to this issue of like distribution shift that we were talking about before, if you have to do this off policy evaluation, it's going to be very high variance if you want to do it directly from data. So you can't just hold out a validation set to do this evaluation. You really need something more like a simulator to get low variance evaluation results of policies that are different than the policy that collected the data. So the benchmarks that I'm going to talk about and the ones that most people work with basically run on top of simulators, and then at test time, they use the simulator to evaluate the new policy with lower variance. So they can have a better understanding of what algorithms are actually helping. And then the second problem is you need to choose the behavior policy. So once you have the simulator, that's not enough in and of itself. to create a benchmark problem for offline RL, you also need to choose the policy that collects the data set. And choosing this policy will sort of give you very different results. So depending on the policy you choose, you'll see that different algorithms will perform better than others. So it's sort of a matter of sort of deciding which types of policies are more realistic that would sort of give us more useful information about which policies are best. Or in some cases, it's just a matter of which sorts of behavior policies are potentially more natural or more easy to collect data from. Okay, so with those sort of caveats in mind, let's talk about a few of the ways that people have been benchmarking things. So in discrete actions, one of the main benchmarks has been just on the Atari domain, which is sort of standard from the online RL literature, where people train online agents in this Atari environment. And basically, in the offline case, we sort of use the same simulator, but have to choose a behavior policy to collect the data. And in this case, the standard benchmark that has been used in literature the last few years is to use the replay buffer collected by an online agent, namely the DQN agent, that's being trained in that environment. So what happens when we sort of test a few of the algorithms we considered earlier against this benchmark? So here's some just results on a few different games that we ran ourselves. So this is just comparing behavior cloning, which is just attempting to use supervised learning to imitate exactly what the behavior did, using BCQ, which is one of the algorithms we talked about earlier, using CQL, another of the conservative Q learning that was discussed earlier, using pessimism, and using DeepSPIB. And here, pessimism and DeepSPIB rely on these uncertainty estimators, and here we're using a neural uncertainty estimator. So maybe one of the main things to point out on this benchmark is that pessimism fails pretty miserably, because going back to what Romain said earlier, finding an uncertainty estimator, especially in these high-dimensional image-based state spaces, is very difficult. And so this uncertainty estimator is not very good, and this causes pessimism to fail. Now, DeepSPIB uses the uncertainty estimator, but also is using it as a mechanism in this sort of conservative algorithm, so it's a little bit less brittle to the sort of failure of the uncertainty estimates. But generally, you see that sort of CQL has fairly strong performance, and BCQ is doing sort of slightly worse than SPIB. Now, another sort of scenario is when we have continuous actions. And here there's this recent D4RL benchmark has been very influential. So now some of the algorithms we talked about don't have, like SPIB, for example, don't have analogs in the continuous action spaces. So we'll consider sort of a slightly different set of algorithms here. And we'll also sort of consider a slightly different set of behavior policies. So I'll just go through three of them here. So the first one is they consider these Mujoko control domains. So these are domains where you're attempting to control a locomotion of sort of a simple simulated robot. And there, the behavior policies that they use to generate the data sets are snapshots of, again, an online agent, in this case, soft actor critic, being trained on that task. Another set of environments and data and like behavior policies is in these maze navigation tasks, where the behavior policy is generated by a hand-coded policy with random goals. So this means that these policies have much broader coverage of the state space because they're not being optimized to attempt to solve the same problem that we're trying to solve in the offline RL problem. So in this case, we're using data that sort of is broadly collected to cover a lot of different things and trying to solve one specific problem. And then another sort of component of the benchmark is some human collected data on robotic manipulation tasks. So these are sort of, where the maze task had sort of been designed to have very broad coverage, these sort of manipulation tasks have very narrow coverage because they're sort of human generated data. So it's very much only covering a small part of the state space. So let's see sort of what happens to different algorithms on these different types of environments, which provide sort of different challenges. So here's the results on the gym locomotion tasks across sort of a bunch of different data sets. So they collect sort of several of them, and I have the mean plotted all the way at the right. And here I'm just comparing BC, which is sort of behavior cloning, sort of just trying to copy what the behavior was doing, versus BCQ, which is sort of one of these conservative algorithms, versus a one-step variant of BCQ, So using early stopping and only doing one step around the loop versus CQL. So you can see here that one step and CQL do about the same, and they both do much better than this BCQ or BC algorithms. So this is basically saying in these environments, the data distribution is pretty, doesn't have a lot of coverage. And as a result, things like the one-step algorithm are actually very effective. Now, the ant maze task is very different, right? Because the ant maze task, we had a policy that was designed to have very broad coverage. And as a result, the CQL algorithm actually works much better than the others in this case. And there's actually even some more recent follow-on work that gets even better results than the CQL algorithm, but using sort of similar ideas at a high level. And then on these adroit sort of manipulation tasks, we see that actually CQL does sort of worse, and sort of in this case, one step is the strongest of the algorithms, because in these cases, the data set is sort of very tightly concentrated around the demonstrations and does not cover the state space very well at all. So trying to do something more aggressive, that sort of is what CQL is trying to do, ends up not working and suffering from these issues of variance, trying to evaluate policies that are too different from the behavior. Okay, so that's sort of just a very brief summary of sort of some of the benchmark work that people have been doing trying to actually implement these algorithms. And now I'm going to toss it back to Romain to give us some concluding remarks.
Thank you, David. Yeah, so we did it. We finished it, almost. So a bit recap. So we introduced the basics of offline reinforcement learning. We motivated that non-specialized methods are insufficient to deal with it. We proposed the Bayesian policy iteration framework to build a cartography of the existing offline reinforcement learning algorithms. And we presented multi-MDP, pessimistic, conservative, and early stopping algorithms. And we made a quick overview of the benchmarks in the literature. So now I want to go back to beyond offline reinforcement learning and repeat what maybe I've said before, that generating a single policy from data is actually rarely the end requirement, the end task. Sometimes we want to iteratively collect more data, and in a multi-batch reinforcement learning way. Sometimes we also want to allow for fast online adaptivity. And yeah, these settings, as I said earlier, are harder to standardize, but clearly a big opening for future work. And I would love to work on that on a very concrete tasks in order to develop them. Okay, so now it's really over. So we've had many questions that we tried to answer in the chat. You may also contact me later by email.